course, just hang up the pens. Let me introduce today's speaker. So today we're very, very happy to have Professor Jeff Filippini from the Department of Physics. Jeff was an undergrad at Harvard. He got his PhD from Berkeley. He was a postdoc at Caltech. And now, since for a couple of years now, he's been professor here at the University of Illinois. Jeff works mostly on CMB experiments, particularly balloon-borne experiments. So if you want to hear about that, maybe you should ask him later. But today, he's going to tell us about the hidden universe, dark matter, and dark energy. So let's welcome Jeff.
Make sure all my microphones are on. Folks hear me? Okay, well, thank you very much for coming, and thanks, Peter, for the introduction. And so, what I thought I'd tell you a bit about today is kind of an unusual part of astronomy and astrophysics. So when you think of astronomy, you think of people looking up with telescopes, looking at stuff out there in the universe. So I'm going to be telling you about the parts of astronomy and astrophysics that are things you can't see through the telescopes. So you might have heard of these two words I've got up here on the board, dark matter and dark energy. So these are terms for things that we don't understand that seem to be the dominant forms of matter and energy in our universe and control our universe's evolution, the formation of large things like galaxy clusters, things like that. And so I did my PhD work on an experiment to look for dark matter. And I remember if I sat down next to someone on an airplane and they made the mistake of asking what I did, I would say, I look for dark matter. And they'd say, really? Is that stuff real? What's wrong with you people? There's invisible stuff out there. So what I want to spend most of my time on today is trying to convince you that why people believe this seemingly crazy thing, that the bulk of the universe is stuff we can't see and stuff we don't understand. And so I'm going to spend, I listed both dark matter and dark energy. I'm going to spend most of my time on dark matter, and time permitting and stuff, I'm going to talk a bit about dark energy at the end. This is kind of fitting. There's more to say about dark matter. Dark energy is even more mysterious. But I'm happy, I hopefully will spur some questions from the audience, and we can take it from there. Okay, so we start with a question. Big question, one of the biggest questions that's ever been. What is the universe made of? So this is an ancient question. This is a question people could have asked thousands of years ago, and they did. And people have come up with all kinds of answers. So if you were asking some ancient Greeks 2,000 years ago, they would have told you, the universe is made of four things, four elements: earth, air, fire, and water. Those of you who are fans of the TV show Avatar will recognize the particular graphics there. But this general idea, this was suggested in the 5th century BCE by a guy named Empedocles, but the same kind of idea was circulating in the ancient world. So you'd find similar ideas before in Babylon, Egypt, India. China had a similar idea, but there were 5 essences. Things like this. So this was the dominant idea. The universe is made of some combination of these things. And then science happened. And science sort of led you eventually, through fits and starts, gets you to around the 19th century. You've got high school chemistry class. You've got this idea that things are made up of atoms. People learned in the 20th century what atoms are made of. There's protons and neutrons in the middle, electrons orbiting. And they have this beautiful periodic table of the elements describing all the different kinds of atoms. Helium, hydrogen, carbon, iron, uranium, all kinds of things like that you'll have heard of. So this was the idea in the 19th and early 20th century. What is the universe made of? Things on this chart. Well then, in the 20th century, a bunch of people spent a lot of time breaking things together, breaking things apart in things like particle accelerators and laboratory experiments, and found that, protons and neutrons have constituents with the funny name quarks, and there are a variety of particles that are similar to the electron, 4 different forces, a whole range of things that if you want to hear more about, you can hear about at next month's talk by Professor Martinez. This is the standard model of particle physics. So the answer at the end of the 20th century is, what is the universe made of? Things in this table. Okay, very, very satisfying. These are all laboratory tests. So this is the laboratory answer. But I asked you, and we've had a lot of triumphs on this recently, a giant particle accelerator, a recent Nobel Prize for identifying the very last particle on this chart, the Higgs boson. And again, I'm sure you'll hear about that more at Verena's talk next month. But we can instead ask what the universe is made of by looking at the universe, looking out. So, you go out on a nice day and a nice clear night, go far away from the big city lights of Champaign, and I mean, I guess we'd see somewhat fewer mountains if we were to go out in the prairies, but on a clear night, you'd see the Milky Way, you'd see thousands of stars. And when you look at this, you can see some of the things, like what's the first thing someone thinks of? What is the universe made of? What's out there that we see? Stars, the big bright things we see through telescopes, all those little pinpricks. We see thousands of them. There are hundreds of thousands in the neighborhood. There are hundreds of billions in the galaxy, hundreds of billions of galaxies, a huge number of stars. Anything else we see in the picture? There are planets. We don't see them here, but we're standing on one, so I guess we do see them here. Planets, so rocky stuff. What else? The edge of the galaxy. And what you're seeing there are clouds. Clouds of gas and a little bit of dust. Those are the materials that form stars. That's right. You see space, you see empty. So I'll cut you off here. These are basically the things that astronomers see through telescopes. They see the gas, they see the dust, they see the stars, and they see the planets. And astronomers spend a lot of time counting these things up. And you get a pie chart kind of like this. Stars form this part of the pie chart. They're actually not that much of the stuff we see through our telescopes. And the stuff like the heavy elements, things like planets, are a very, very tiny fraction of the material in the universe. Much more is that gas around here, both the visible parts and the invisible parts. Astronomers have found various ways to find these gas clouds in the universe, and it turns out the gas clouds outweigh the stars by a very large factor, by a factor of 10, or 5 maybe. And then one more thing from that standard model, these mysterious neutrino particles that Professor Liang Yang gave a Saturday physics talk on some time ago, those turn out to be kind of substantial too. But this is our chart of the things from the standard model. This is what's out there in the universe. Mostly gas, a sprinkling of stars, and a tiny, tiny dusting of other stuff. But that's not what astronomers think the universe is made of today. All those things that I just showed you, I can make a bigger pie chart where that's only 5% of the total. And that 5% includes, that chart I showed you, includes all the things in the standard model of particle physics, all the things that we know anything about, to be frank. But what else is there? Well, it turns out, as near as we can tell, and I'll explain the evidence behind this, about 5 times as much of the universe's contents is something else, dark matter, something that we feel its gravitational impact. We see how it affects the flow of matter in the universe. But we don't know what it is, and it doesn't seem to be any of these things, as I'll explain. But what it does do is it holds large structures like galaxy clusters together. And I'll explain this picture a bit later. But around the year 2000, there was an even more amazing realization, which is that about 2/3 of the universe is something else, dark energy. And all we know about that is it makes the universe's expansion go faster and faster. And so the big problem, one of the big triumphs toward the end of the 20th century was realizing that the universe is not made of the same stuff we are. And a big challenge for the 21st century, and hopefully maybe beyond, is to figure out what these things are. So there's a lot of thinking going on. We now have this beautiful pie chart. There are numbers after the decimal place. These are precision numbers of what the universe is made of, but we have no idea what these pie chart pieces are made of. And to skip ahead, we have, this sounds kind of nuts, that there are these things, we don't know what they are, but they constitute the bulk of the universe. But we actually have a lot of lines of evidence from looking at the universe today, looking at baby pictures of the universe as it was, how it gets in between, how it's grown over time, and various catastrophic events in the universe. There's various things we see through our telescopes that convince us this is right. And that's what I'll spend most of my time trying to talk about and trying to convince you of. We really do know how much of these two things they are. They do seem to be real, even if we don't know what they are. Okay, so first we'll start with that first one, dark matter. So what's dark matter? So to think about dark matter, we have to ask, how can we detect something that we can't see? Astronomers are all about telescopes. How do we detect something we can't see? And so the first example we can give of that is from quite a while ago. The first example of dark matter, the first matter that was detected without seeing it, was a planet, Neptune. So Neptune was discovered around 1846. It was discovered, 160 some odd years ago. It was discovered about 1 Neptunian year ago. The 1 Neptunian year anniversary of Neptune's discovery happened in, I think, 2015. It's a very big, far out there, slow orbit, 160 years to go around the sun. Very, very dim and hard to see. But it was predicted. It was predicted by this guy, whose pronunciation of his name I will butcher, but Urbain Le Verrier. It was at Paris Observatory, who did some calculations involving gravity. And he saw that in 1846, it had been about one orbit of Uranus, since Uranus was discovered by William Herschel. That's the next planet, the next innermost planet. And he found that Uranus, for part of its orbit, seemed to be doing roughly what it was supposed to, but then it kind of sped up a bit at one part of its orbit in a way that nobody expected. Like, we know how it should orbit. Why does it go a little faster for about 20 years in its orbit? And then for the next 20 years, it was a little slower than it should have been. And so this guy Le Verrier thought about this a while and said, aha, the way I could explain this is if there were another planet, there were an eighth planet, farther away, whose gravity was pulling on it, who was orbiting even more slowly, so that Uranus gets sped up a little bit by getting pulled by this planet, a tiny, tiny amount. And then when it passes this planet, it gets slowed down a tiny bit. So he did these calculations. There were a couple teams, also one in England, working on this. And then a guy named Johann Galle, whose name isn't mentioned quite as much, actually got, because no one respects the experimentalists, right? It's all these theorists get all this credit for doing this calculation and finding, and he looked in the right place, and son of a gun, there's a planet. We've actually sent a space probe there and taken beautiful pictures of it, Neptune. But this was an amazing feat. This was predicting, with his mind alone, with calculations and measurements, predicting the location of a new body detected only by its gravity. And then we saw it, and then it was there. And you can do this kind of thing more broadly. So now think about the solar system. Suppose you couldn't see the sun. Kind of hard to imagine, but suppose you couldn't see the sun. But eventually you build sufficient instruments, you can see all these planets through infrared or something like that, and you see them all orbiting something. You would still know the sun was there, because it's gravitational pull. Those planets, if those planets were just sort of hanging around, they would move off in a straight line. They would spin off in a straight line. Ooh. Okay, so then, this is a little tangled. There you go. So what keeps them in their orbit, right? So if the planet is swinging around, I have to pull on this string to keep the ball from flying away, right? I need to pull on this string, and so something must be pulling on the planets to keep them in these orbits, and that something is the gravitational pull of an object in the center, the sun. And you can actually measure this, and I will show, I believe, only 2 equations in this talk, but I show this for the benefit of anyone who likes high school physics. You can actually do this calculation. You can say, I know how fast the planets are moving, and I know how far away they are. Their gravitational force the gravitational force must equal the force necessary to keep them in the orbit, and you eventually find that you can weigh the sun. The mass, your estimate of the mass of the sun depends on the speed of the planet and its distance from the center. And that's it. You don't need to know the mass of the planet and to still figure out the mass of the thing it's orbiting. So we could, even if we couldn't see the sun, we could not only know it was there, but we could weigh it incredibly precisely from seeing the orbits of those planets. And that leads to the 2 ways we try and learn about what the universe is made of. 2 ways to weigh. And our 2 ways to weigh are we can either look out with our telescope and count things. I see this many stars, I know how big a star is, I add them up, that's what the universe weighs. Or I can do something more like Leverrier did, and I can look at how gravitational forces are influencing the motions of things in space. And use that to say, if Uranus is speeding up and slowing down, there must be something pulling on it with gravity. And similarly, other objects in the universe, if they're doing things we don't expect, there must be something pulling on them, again, with gravity. So let's get to a system bigger than the solar system, a galaxy. So a galaxy, this is a beautiful picture of the Andromeda galaxy. So this is a nearby big galaxy, sort of a twin of the Milky Way, about 2 million light years away, like we see it as it was 2 million years ago. And it is actually quite a bit bigger than our galaxy. There's about 1 trillion stars, 1 million stars in this enormous whirlpool of galaxy, a whirlpool of stars. Stars being born out here, old stars in the middle, little tiny sub-galaxies orbiting the thing, remarkably complex system. And we're only 2 million light years away. We get a wonderful view of it. So then we get to a rather famous scientist. There are several scientists who studied Andromeda and other galaxies, but the one I'll talk about today is Vera Rubin. and her colleague Kent Ford. So they were at, I think, the Carnegie observatories at the time. And they were trying to figure out, remember, I look back at this, I'm seeing all of these stars very slowly are orbiting in this galaxy. It's like a giant solar system, a little more complicated because there's like, a trillion stars. But you could figure out how much this galaxy weighs by figuring out how much gravity is necessary to keep those stars moving in their orbits. And to do that, you need to figure out how fast they're all moving. If you knew how fast all of these stars were moving, you would know how much gravity is needed to keep them in those orbits. So that's what Vera Rubin did. So she took this Andromeda galaxy, and she marked off a whole bunch of gas clouds, orbiting clouds of fluff going around that galaxy. So some of them are moving, so as the galaxy spins, some of them are moving toward us, some of them are moving away from us, so that as this object spins. And so she could use spectroscopy. So she could measure, for each of these gas clouds, measure various features in the light that comes from it. And you may have heard of the Doppler effect. So the Doppler effect is when you have a police car siren. It makes this sort of meow sound when it passes you. The frequency is higher as it goes toward you, and the frequency gets lower as it moves away from you. You can do the same thing with light. And by measuring the precise wavelengths at which these different features happen, the edges moving toward you, the light should appear a little bluer, a little higher frequency, shorter wavelength, and the parts of the galaxy moving away from you should appear a little redder. So you can estimate the velocity of all of these clouds. And they developed a fancy instrument, precision measurements to measure what are the rotation speeds of all of these clouds. And they discovered something kind of remarkable. So if you plot out, this is for a different galaxy, but they plotted basically the same thing for Andromeda and actually for many other galaxies, and found that usually what you get is something like this. If you look at where all the light is, the light is mostly in the center of the galaxy. That's where most of the stars are. So what you'd expect is that objects way out here should be orbiting. What matters for setting the speed of the orbit is how much mass is inside the orbit. And so objects out here, as you get farther and farther away, you get farther away from the bulk of the mass in the galaxy, the speed should go down. Just like Pluto moves slower than Mercury, because it's farther and farther away from the cluster of mass. So you expect, from looking at the stuff you can see, that the speed of these clouds should have gone down as you go out to very far outskirts of the galaxy. And what they found instead was the speed is kind of flat. So that isn't consistent with the mass that we see in the galaxy. It must be that there's some more mass, that there must be, as you get farther and farther out, there must be more and more gravitational mass, as if there was some larger cloud that the galaxy was just a little sprinkle in the middle of. There's some larger cloud that is providing extra gravitational pull. The difference between these is dark matter. The difference is there must be some mass providing more gravitational pull than what we can see. And this was a remarkable discovery. And there had been similar work that people hadn't really appreciated in 1939 by a guy named Babcock. There were various people who looked at things like this. But this was the data that really convinced the community, convinced the world, that these galaxies don't rotate the way that would be expected from just the matter you can see. There must be more matter. And so to give you an illustration, like if you take a galaxy, a spiral galaxy like this is how it would rotate, incredibly sped up, of course, how it would rotate if there were only visible matter versus dark matter. And you can see if there's only visible matter, the outer edges of the spiral arms move extremely slowly. Whereas with the dark matter, the outer edges are actually moving pretty quick. So you can kind of compare that spot to that spot. And if you stare a while, you can convince yourself the rotation pattern of these is very different. And so this distinction, by measuring that difference in the speed profile, that tells you that there's more stuff. There's more stuff. Otherwise, those fast-moving stars would fly away. There must be extra force holding them in place. And this actually gets back to some earlier work. So there was some work on larger structures, galaxy clusters. So remember I showed you that giant galaxy, Andromeda, with 1 trillion stars in it orbiting. Well, this is a galaxy cluster seen with the Hubble Space Telescope. Each of these objects is a galaxy with millions, billions, even a trillion stars in it. So this is a collection of dozens, some of them have hundreds of galaxies, all orbiting and moving around one another in a cluster, bound together by gravity. So again, you can look at these and ask, aha, how much gravity is needed to hold these galaxies in place so that they don't fly apart, so that the cluster doesn't fly apart? And an astronomer at Caltech, everyone loves this picture of him. He was apparently kind of a irascible, grumpy type. Fritz Zwicky, who was German-Swiss, back in the 1930s, so 40 years before what I just showed you, had been studying galaxy clusters, particularly one called the Coma cluster. So if you look at this doesn't look like much, but you see how there's a whole bunch of the galaxies that are kind of yellow-colored. Some little tiny specks, some big ones. All of those are galaxies. If you zoomed in on them, you'd see that each of these little yellow specks is an entire galaxy. And this is a cluster of hundreds of galaxies, all moving in different directions, like a little cloud. Or imagine a swarm of bees buzzing around each other. So you can ask, how fast are they moving? And he went and measured how fast they're moving, and it turns out they're moving too fast. He concluded that there must be hundreds of times more matter than what he could see from the galaxies. Otherwise, they would all fly apart. There must be much more gravity holding them together. And he gave this a German name, I can't pronounce it, Dunkelmaterie, but dark matter. So this was the original discovery of astrophysical dark matter. It wasn't appreciated or really accepted for decades longer, but it had been seen on cluster scales, and then Rubin and Ford saw it on galaxy scales. A whole bunch of stuff out there. And so he gave this ratio of 500. Today we would say there's 300 times more matter than you can see, but actually a lot of that is gas. So there's actually only a few, about 5 times more matter than is ordinary matter. There's something else. So one thing that'd be nice is it's very unsatisfying to not be able to see this. But we do have one way to sort of see the dark matter. And that is using a trick by the gentleman on the right, Albert Einstein. So he came up with this idea presented in 1915 of general relativity, the idea that gravity bends space and time around a heavy object, that this is how gravity works. And so what happens is, to give you an example, I like to show this picture. It's kind of pretty. Right. So his view was that space and time were kind of like a stretchy sheet around in the universe, and a heavy object distorts the sheet. And then what we perceive as orbits and things like that are actually that an object that moves past will move in a curved path because space is bent. Heavy objects distort space-time, and that affects the way other objects move. And one of the things Einstein noted was that also affects the way light moves. A light ray from a distant object will bend around a heavy object. So what does that mean in practice? That means is that if you have some really big galaxy cluster that you can see, there are also very distant galaxies behind it. And those galaxies, their light is bent by this galaxy. This giant galaxy acts like a lens. It distorts the image of what's behind it. This is called gravitational lensing. And that provides an interesting way. You can tell how heavy this object is by how much it distorts the image of things behind it. And so a nice example of this is another galaxy cluster seen with the Hubble Space Telescope. So the big yellow thing is the galaxy cluster. But if you look closely, you'll see things like that. Little streaks and arcs. Funny, curly, thin shapes. Those are actually galaxies themselves. If you could see them normally, they would look like these. They'd look like kind of lumps. But their images are stretched out into little arcs by being distorted, passing by this big mass. So those little arcs are showing you there. You see how they're all sort of circling this big, heavy mass. And by measuring their shapes and how much they're distorted, you can tell how much mass there is. And in fact, you can map it. You can say that the stuff in that galaxy cluster must be distributed in a big cloud kind of like this. And so in this indirect way, we can see the dark matter. We can see that the mass of this galaxy cluster is in some giant cloud, and the galaxies we see are little bright objects embedded within this much more massive cloud. So gravitational lensing lets us see these halos. And I say halos, this is our picture of what dark matter looks like in some sense. If we had dark matter glasses and could see it, you'd see that a galaxy is embedded in a big cloud of something else. A galaxy cluster is embedded in a big cloud of something else. And eventually you'd get to what's called the cosmic web, that all the galaxy clusters and all the galaxies are in their own little lumps of dark matter. And those lumps of dark matter are linked together like a three-dimensional web. There's a webwork of dark matter filaments filling the universe, and at the junctures are big galaxy clusters and galaxies. So if you could see in dark matter goggles, you would see this massively complicated structure. But we only see the little bright pinpricks within it. So that's the image I showed you at the beginning of the talk. This is a simulation. This is a computer simulation of what the universe would look like. But it's consistent with our observations. Our observations through our telescopes, we do see galaxies lined up in this way on large enough scales. We can see them sprinkled across the cosmic web like this. But the web itself is mostly dark matter, stuff we can't see. So that's kind of the evidence from the modern universe. This is, we look at the universe today, we see the way matter is distributed, we see the way gravity moves objects in galaxies and galaxy clusters. We see that there's this invisible stuff. But we can also see it another way, which is by looking back at what effect it had on the growth of the universe. So if you look back, so this is a schematic of what we think the history of the universe looked like. The Big Bang Theory, the part that isn't the sitcom. You start out at some point in the past, on this very weird temperature scale, time scale, you start out in the past in some very hot, dense state, and the universe has been expanding and cooling ever since. And as the universe expands and cools, it goes through various phases of existence. First, it's so hot that we're in the domain of particle physics. Then it cools off. We're in the domain of nuclear physics, atomic physics, and then finally you reach this magic point about 400,000 years later than the Big Bang, when the first atoms form. The universe finally becomes cool enough for electrons to fall into orbit around protons. The universe goes from being opaque, light can't get through this hot ionized material, to becoming transparent. So the universe goes from bright to dark at this very sharp moment. And then eventually things grow under gravity, and we get all the things astronomers look through in telescopes. So all of astronomy is way on the right. But there are two things we can look at that are relevant for dark matter. Two signatures that the history of the universe has given us. One is that glow, that moment when the universe goes from being opaque to transparent. That's the farthest back we can see. And the other is this period back here when nuclear fusion happens, when the universe was as hot as the center of a star. In the center of a star, little atoms are fused together to form big ones. And that happened in the early universe as well. And the two signatures we get from this, I'll just say quickly, in those first 3 minutes, fusion happens in the early universe. Protons form into heavier nuclei, particularly heavy isotopes of deuterium, heavy hydrogen, and helium. So the amount of helium and heavy hydrogen that we have in the universe today depends on what the conditions were in those first minutes. And in particular, it depends on the density of protons, neutrons, and electrons, the density of ordinary matter. And you can do measurements where this is the density of ordinary matter in some crazy units you don't care about, and this is the amount of helium, the amount of deuterium, funny isotopes of hydrogen and helium, and lithium. So various light nuclei. And they depend, the amount that we see today depends on how much protons, neutrons, and electrons there were in the early universe. And so we can measure, by knowing how much of these things there are, how much ordinary matter there was. And that's one of the ways we get that funny 5% number. That this tells us there wasn't that much ordinary matter around back then. About the same amount as we see today, but this dark matter must be something else. There weren't enough protons, neutrons, and electrons. So this is why people say dark matter isn't just gas we can't see. It must be something that isn't protons, neutrons, and electrons, because that would have changed the fusion processes of the early universe. And I list, because it's fun, the paper that discussed, one of the early papers that discussed this idea was by a guy named Alpher and a guy named Gamov, who decided, because they liked silly jokes, to add Hans Bethe to the paper to get the Alpha Beta Gamma paper. So we know from this that the hot early universe, the fusion early universe, that when fusion was happening, there wasn't enough ordinary matter around to constitute the mass of those big halos we saw, those big dark matter clouds. The dark matter can't be this, can't be the stuff we know. Worse yet, we have this other period, we have this other baby picture. So remember this moment I talked about where the universe goes from opaque to transparent. We can see this with telescopes. This is something I work on today. You may have heard of something called the cosmic microwave background. This is the glow of that hot early universe, that moment when the universe went from opaque to transparent. So if you had eyes that could see in microwave radiation, so you could see 100 gigahertz radiation rather than visible light, you would literally see a wall of fire surrounding us. Every direction you look, you would see a glow. And that glow is literally the afterglow of the Big Bang, the glow of the hot plasma of the early universe. And when you zoom in on it, you see there's little hot and cold spots. This is a map of the whole sky, flattened out. Another way to look at this is there's like the beach ball version, where you make a map of the sky, every direction you look, that shows you where the pattern of hot and cold spots are. And if you could see that, so those hot and cold spots are literally like ripples in a pond. Those are vibrations and waves that were moving through that plasma at that moment. And just like from looking at ripples in a pond, you can tell something about the properties of the water, or by listening to a bell, you can determine the properties of the metal that's doing the ringing. You can determine whether it's a brass bell or an aluminum one. You can determine if it's a big bell or a small bell from listening to the sound. Here, the ripples, the sound we see of these ripples ringing through the early universe tells us about the properties of the material of the early universe, that hot plasma. And again, it tells us that most of the matter, about 80% of the gravitating matter, was not protons, neutrons, and electrons. The protons, neutrons, and electrons interact with light. They interact with this glow. The dark matter just sloshes around under gravity and doesn't interact, and so we can tell the difference. How much of the matter is interacting with light, how much of it isn't. And this tells us that the universe, again, was mostly something else at 400,000 years earlier. And these numbers agree with the numbers we see today. So we have a very consistent picture. The universe has always been made of 5% stuff we see and a bunch more. And you can even do better. So people do simulations. You start off with the universe with little hot and cold ripples, those little tiny spots. So those spots I showed you, the red spots and the blue spots, they only differ by about, the hot spots are only 10 or 100 parts per million hotter. So a tiny fraction of a percent hotter. So it's very smooth with little tiny ripples. But the places where it's a little hotter, there was a little more stuff. And over time, the rich get richer, and those gather more material under gravity. And those little over-dense spots became the seeds of galaxy clusters today. And people have simulated this. So you can run a simulation as time goes on. This is 70 million years after the Big Bang, 80 million years after the Big Bang. And you can see over time, this very tiny over and under densities glom together to form that cosmic web I talked about. So you can see these denser parts are growing together. Eventually, galaxies will be born in these denser parts. So the brighter parts are denser, and you get these voids in between. But in order to make galaxies like we see grow fast enough, you need there to be extra matter around to provide enough gravity to glom that stuff together. If there was just ordinary matter, galaxies wouldn't grow fast enough. This process wouldn't happen fast enough, and we wouldn't have, it has been only 14 billion years since the Big Bang. That isn't enough time to produce galaxies unless there's extra dark matter to provide extra gravitational pull. So that's the big story of why people think this crazy thing, that most of the matter in the universe is invisible. It's because we see its evidence in the modern universe. We see its evidence in the universe's baby pictures, that cosmic microwave background I showed you and the light element ratios. And we see its evidence in, we need the dark matter to make the universe grow from the way it was then to the way we see it then to the way we see it now fast enough. That's why people are convinced dark matter is real. But I can give you one other story. So I talked about the triumph of detecting Neptune, how great it was. Like, but someone purely by calculations and measurements could infer the existence of another planet. Well, there was a time that didn't work. So remember this guy, Leverrier? Same guy was feeling real good about himself because he just predicted a planet. No one before or since had ever done that. So someone pointed out to him, well, you know what? The innermost planet, Mercury, does something kind of funny. Its orbit, as it orbits the sun, its orbit is elliptical and the ellipse precesses. So the orbit turns very slowly, 500 and some odd arc seconds per century. So an arc second is a 60th of a 60th of a degree. So a tiny fraction of a degree per century, that orbit turns. And mostly you can understand it from the push and pull of the other planets. But there's 43 arc seconds of turn per century that the most precise calculations could not figure out. And Leverrier says, I got this. I've done this once before. When something moves in a way I don't understand, there must be another mass. And so he predicted there was another planet called Vulcan. There was another planet closer to the sun than Mercury. And his idea was we'd never seen it because it's always right in front of the sun, and so you just never see this planet. And people looked for this for decades. Some people thought they saw it, some people didn't. I want to tell you how much self-control it took to not put a picture from Star Trek on this slide. But sticking with that, people looked for this for centuries, for decades, and they didn't find it. And it turns out that gentleman Einstein explained why. Because remember, gravity is, with general relativity, we found out gravity is actually warped space-time. That bent space-time affects the orbit of Mercury, because Mercury is so close to the sun. And that explains the whole effect. This is one of the ways Einstein knew he'd gotten it right, is because he explained this mystery that had been sitting around for decades about why Mercury moved the way it did. So this was a time where we tried the same thing. We saw something move in an unexpected way, and we said, aha, it's new material, and we were wrong. It was modified gravity. And so people think the same thing about dark matter. There's a guy, Mordechai Milgram, in 1983, suggested, what if we change the force law of gravity? What if we're wrong about the equations of gravity? At some very, very tiny, at some very large scales, it only affects these kinds of measurements. So it only matters like F equals ma, force equals mass times acceleration. What if that law changed at incredibly tiny accelerations? And the details don't matter, but you can make this explain what galaxies do. You can tweak gravity to get galaxies to have flat rotation curves just the way they do. But it's extremely hard to tweak gravity to do that and get gravitational lensing right, and get the cosmic microwave background patterns right. And there's no theory behind how this works. And it's hard, I forgot to mention, it's hard to make those galaxy clusters work. So you can explain Vera Rubin's observations, but you can't explain Fritz Zwickie's observations at the same time. Those things don't fit together naturally. So you can explain this one thing, but you can't explain all the rest. But still, people have been trying for a long time, like maybe we're wrong about gravity, maybe we can fix it. And then, so let's give a very nice observation that convinced people that this wasn't true, that dark matter was real. This is a galaxy cluster. I'm sure that to a real astronomer who looks through telescopes all the time, not me, this is obvious that this is a galaxy cluster. But looking at it, it's like it's a bunch of galaxies. But if you look closely at them, an astronomer could tell you that these are actually two clouds of galaxies that are bound together gravitationally. And one thing we can do with this is we can look at where the gas is. We can see the gas. Those clusters have a lot of gas in them, more gas than stars. And we can see this funny shape to the gas, which we see in its X-ray glow. This sort of a shock wave. And what people figured out is, aha, what happened here is there were two galaxy clusters. It's called the bullet cluster. See the bullet. One galaxy cluster literally smashed through the other one. So two galaxy clusters collided, and they just went floosh through each other. The galaxies basically are spread out. They don't hit each other, but the gas had friction. The two gas clouds had friction, and you can see it sort of the gas got left behind, bunched in the middle. The galaxies are over here, but the gas had friction as it passed through and got left behind in the middle. But remember what I talked about gravitational lensing. There are tiny distortions of the background images of the galaxies. And statistically, you can study them and figure out where the mass is. And this is where the mass is. Those are the two galaxy clusters. But that means that, remember, most of the ordinary matter is gas. And the gas is in the middle. So this tells you that most of the ordinary matter is at the red. But most of all of the matter is at the blue. So when those two galaxy clusters collided, the gas got left behind in the middle, but something that doesn't feel friction, something non-interacting, passed right through. And so the animation of how people think this works is the galaxy, the gas and the dark matter were together at the beginning. When they pass through each other, the gas falls behind because of friction. The dark matter just sails right on through. And that tells you the ordinary matter and the dark matter are two different things. They're actually in two different places. And this was touted as final definitive evidence for dark matter, because I actually finally took a picture where the dark matter's over there and the ordinary matter's over here, the bullet cluster. And there's since been, there's like a dozen systems like this that have since been discovered of these galaxy collisions where the dark matter gets segregated from the light matter. So yeah, dark matter. So we have all this evidence from a variety of places, modern, ancient, evolving, but we have no idea what this stuff is. So let's talk a couple minutes about what the stuff might be. So here's our list of things of what dark matter could be. And, well, we know that whatever it is, it must be stable. It's got or long-lived at least. It was there in the early universe. It's still there today. That rules out most things. We know it doesn't interact much with ordinary matter. Because, well, one, we would have seen it, and it passed through itself that way. Those two clouds pass through each other. There's not much interaction. That rules out most other things. We're left with the neutrinos. But neutrinos will move very fast. They're relativistic. And whatever it is, for technical reasons, must be moving slowly. Otherwise, little tiny galaxies, we see some very tiny galaxies with only a few thousand stars in them. Those galaxies would not form. Those galaxies would not form if it was made of tiny, light, fast-moving particles. So we've ruled out everything in the standard model. So now we're in trouble. But there's plenty of new ideas. Theorists are very clever. For every theorist who's thought about the dark matter problem, there is at least one new idea of what dark matter is, usually many. And there's a whole landscape of, the names don't even matter here, of what different theoretical ideas for what new physics could explain dark matter. And so people look, but I'm an experimentalist. I want to look for it. How am I going to experimentally tell what this is? One way is we try and smash things together in a particle accelerator and see if we make some of these new particles. And folks here and elsewhere work on this. This is the Large Hadron Collider, miles across, big particle accelerator, enormous detector. We smash stuff together and try to find whether we generate any new particles. And if we do, maybe that'll tell us something. Maybe some of those new particles will tell us something about dark matter. We also can look for dark matter annihilating or interacting in some fashion out in space. Maybe it does interact a little bit. Maybe it annihilates or decays. And there are telescopes that the idea is you would see a glow in gamma rays, little pinpricks from all of these little galaxies out there would each be glowing in dark matter from the dark matter clouds in their centers. So people look for this with space and ground-based telescopes in various ways. It's called indirect detection of dark matter. You're not going to be shocked to learn we haven't seen anything yet. You would have heard. There have been various people saw strange things that, oh, maybe that's dark matter, but so far none of them has survived further scrutiny. The kind of experiment I worked on is called direct detection. So the idea there is, I'm not going to, making dark matter sounds hard at an accelerator. And telescopes are hard too, but the dark matter is around us. We are embedded in a cloud of dark matter. Dark matter should be passing through our body every second as the Earth moves through this cloud. So if we can build the right detector, every now and then a dark matter particle will knock a nucleus of an atom out of place. And with the right detector, you should be able to tell. And so you have to shield this detector so that nothing else gets to it. So you bury them deep underground. This is a beautiful summer's day in northern Minnesota, at the head frame to the mine that I worked in graduate school. Only sometimes they didn't put me in the mine for the entirety of grad school, but I spent quite a bit of time there. So I worked about half a mile down on fancy detectors to look for these rare pings of mysterious particles from space, if they're there. This is me on top of my experiment in cleanroom garb. Important fact, this is not a dangerous place. I'm not wearing those clothes for my protection. I'm protecting my detector from me because I'm radioactive. And I'm sorry to say it, so are all of you. There is radioactive potassium, radioactive carbon. There are radioisotopes. There's 8,000 radioactive decays in each of your bodies every second. And you basically get on with life. It's fine. But our detectors would see it. A drop of spittle from my mouth on one of those detectors would be a problem. We would see the pinging of the radioactive potassium in that spittle. So I'm protecting my detectors from me when I wear that garb. And there are many technologies. I worked on hockey puck-sized pieces of, essentially giant microchips, pieces of germanium underground, kept at a fraction of a degree of absolute zero. Other folks work on giant tanks of liquid xenon, and liquid argon to detect dark matter particles. There are also folks who use a very different detector, kind of a radio detector for a different kind of dark matter. And again, no results so far. Well, there's one, but I'm not going to talk about it, that are definitive for dark matter. But new detectors are coming online, powerful new ones, and we'll see what they find. And finally, one of the things that's interesting recently is there are folks mapping out. Remember, we discovered dark matter by the way it causes things to move. So another way to learn more about dark matter is to very precisely monitor how stars are moving. And maybe we'll learn something about how the force depends on distance, or how, if there's anything funny, maybe there's some signature in this. Maybe there's some information we can grab from understanding how it affects the motions of stars. And so there was an announcement a few weeks ago, the first data release from a satellite called Gaia, which is from the European Space Agency, whose job it is to map in 3 dimensions the locations of 1 billion stars in our galaxy. More, in fact. Actually, it turns out no one's done this. Survey the entire sky from space and map exactly where every star is and how they're moving in 3 dimensions. And there's already data taken. We're already analyzing this. Maybe we'll learn something about dark matter in our own backyard. So we're looking for dark matter every way we can, underground, in the lab, and in space in various ways. Still nothing yet. But hopefully, in the coming years, maybe we'll see something definitive, and maybe we'll get some idea of what dark matter is. Yes?
The bullet cluster?
Yep.
I noticed that the bigger one had most of it on the edge, right? Well, the second one had the highest concentration near the center of it still.
So the question was about the bullet cluster, that picture I showed toward the end over here. I have to kind of scroll through to. Yeah, so I think the question is, why is this matter sort of on, this guy have most of its gas on the edge and this guy has sort of more of a fuzzy cloud? I don't know much terribly useful to say about that. It's going to be, the simulations, it depends on how big and fluffy the 2 gas clouds are. Like this galaxy is this cluster is a little more compact, it's a little smaller, and so it was more like a bullet. It was a smaller thing that punched through the big fluffy galaxy cluster, and that means they have different shapes afterwards, roughly. Yes?
So I've heard that there might be a 5th fundamental force, like weak gravity, that can affect the dark matter.
People look for this. So the question was, is there a 5th fundamental force? So I didn't talk about the 4 forces, but there are 4 forces of nature: gravity, electromagnetism, and these strong and weak nuclear forces. But there are people who think about whether there's a 5th one. And a 5th one might solve some of our problems, because you can concoct a theory where the 5th one helps to explain how dark matter behaves. There are ideas in this direction. There are people looking for evidence with very fine measurements of gravity. So far, there is no evidence of a 5th force. So that's mostly what I wanted to say about dark matter. And I've already used up quite a lot of my time. And there's this other thing, dark energy. So I'll go through this real quick so we have time for questions. But the idea here is, what is all this stuff? And this comes back to the idea of the expanding universe. The universe is expanding. Everything is rushing apart from everything else. This was discovered by Edwin Hubble in the 1920s. And there's been a question, how much stuff is there in the universe? There's a critical density of about 10 hydrogen atoms per cubic centimeter. If the universe has more stuff in it than that, then the universe will expand and then contract, like a ball getting thrown up and coming back down. It gets thrown, the Big Bang hurls matter apart, but the matter's gravity eventually draws it back together. Big crunch, it's called. If it has less than this amount, the universe should just expand on forever, like if I threw this ball at escape velocity and it just left the Earth. And there's an in-between case. And these also affect the universe's geometry. What's called a flat universe is the critical case, but I won't talk about that. All the matter I just showed you only adds up to about a third of that critical density. But measurements from the microwave background suggest that the universe is flat. The universe has that critical density, but the dark matter only gets us up to a third of that. So what you'd like to do is actually monitor how the universe is expanding. And so some projects went and started looking at these special kinds of exploding stars out in space, supernovas, type 1a supernovas. They're caused by a little star stealing matter from a big star. This is called a white dwarf, gloms matter from its neighbor, reaches some critical amount of mass, and then blows up. So it's like you're filling to a critical amount. And so all type 1a supernovas, when they blow up with about the same brightness. And when they blow up, that is in this galaxy. That is one star exploding with the brightness that outshines its entire galaxy. So these are incredibly bright events. So this is amazing. You can see these from across the universe. And you know how bright they are intrinsically. So from how bright they look, you can tell how far away they are. So they form a ruler. They let you measure by looking at a lot of these supernovas, by building a robotic telescope that scans the sky and charts these explosions, you can figure out how far away each of those different objects are. And that lets you measure how fast the universe has been expanding over time. And there were a bunch of data points around the year 1998 to 2000. There were some announcements of folks measuring supernovae and putting it on a plot like this. And what they found was the universe seemed to be doing something very, very strange. And I won't explain the details of the plot, but the universe's expansion was speeding up. This is crazy. This is like I throw a ball in the air. I know that the ball should slow down. Even if I throw it fast and it leaves the Earth, it will slow down as it leaves because gravitational pull will slow it down. But apparently the universe's expansion is speeding up. It's like as if I threw the ball in the air and it suddenly sped up and rocketed away. The universe seems to be doing this. The universe's expansion is accelerating. And this is a big deal. It won a Nobel Prize for these three scientists in 2011 for discovering that the universe is doing this insane thing. And I won't talk about this is my other equation, the Einstein field equations. I won't talk about this at all, other than to say that general relativity says that the warping of space-time depends on the matter. Depends on what matter and energy are in the universe. But he also put in this funny term, lambda, the cosmological constant. This is an energy density of space itself. What if empty space had gravity? Like you think of empty space as empty. Empty space has to be empty. How could it have gravitational pull itself? But Einstein said, well, my equations, I could put in this term, and then empty space would have a gravitational force. And it would be a very weird one, because what it would act as a repulsive force. Because it's very strange. Like you imagine if the empty space, as space expands, you get more space. So that new space has the same energy as the old space. There's a weird conservation of energy problem here. It turns out it's fine, don't worry about it. But you get it's a very strange thing for empty space to have energy in an expanding universe. You keep getting more of it. And it produces this repulsive effect, it turns out. He put that in as a fudge factor to make sure because he didn't know the universe was expanding. But now it turns out that it seems to be real. Or something like it is. There could be other new theorists have thought of all kinds of crazy ideas that could do the same thing. But this is very mysterious. The universe is accelerating, we don't know why. We called it dark energy. We give the name dark energy to the energy that is making the energy of empty space, the energy that's making the universe's expansion accelerate. And we have this wonderful plot This is the density of matter. This is the amount of dark matter, the amount of dark energy. The CMB tells us we lie in this orange region. Studying galaxy clusters and the positions of matter in the universe show us we're along this line, and the supernova tell us we're here. And so we know we are there. And that is the pie chart I showed you. The universe is 68% dark energy, 5% ordinary matter, and 26%, or whatever it adds up to, dark matter. So we know these numbers extremely well from many measurements. You might have heard some report recently that dark energy doesn't exist. There were some news articles about this. Yeah, don't worry about it. All they did was they changed the shape of the blue. When you combine all the data, we're still right there. That article was not compelling, shall we say. The way we're trying to learn more about this is to map everything in the universe. And this is a major effort here at U of I, among other places. So we have people, particularly at NCSA, the National Center for Supercomputing Applications on campus, work on this instrument. We have people working on the Dark Energy Survey and on a future instrument called the Large Synoptic Survey Telescope, LSST. This telescope maps a huge fraction of the sky in great detail to know where all the galaxies are, to help us understand that cosmic web. And by knowing where things are and how they're moving, we might learn something about the forces that are causing them to do it. Something about dark energy, something about dark matter. LSST will map the entire sky every few nights. It will generate terabytes of data, phenomenal amounts of data that, frankly, astronomers have no idea how they're going to analyze. But one of the institutions in charge of figuring out how to analyze that giant torrent of data is NCSA here at U of I. And so this is going to be a huge challenge, and a lot of the work is going to happen here. How do we analyze the data from these massive surveys of literally the address of every galaxy in the universe, or as much as we can see? Big problem. This will teach us a ton about astronomy, but it will also hopefully teach us about dark matter and dark energy. And there are space-based versions as well. There's a satellite called Euclid that the European Space Agency wants to put up around 2020 that will similarly be mapping large amounts of the sky in great detail from space. And one called WFIRST that is going to come along a few years later from NASA to do related kinds of work. WFIRST was in the news a while ago because one of the ways we're building this is that it turns out, you might have heard of spy satellites, the National Reconnaissance Office, very, very secretive. They basically called up NASA a few years ago and said, oh, you know, we have a few old large mirrors for a space telescope lying around. Would you be interested? And you say, why do you have that? No reason. And it's because, of course, they build big telescopes that look down. And they had some spare mirrors from the old, outdated models. And that's partially what's going to go into building this great new instrument. So, looking ahead, this is what we got. We don't know what it is. So, we have this great triumph. We know what the universe is made of. Go team. We don't know what most of it is. Little embarrassing. But there's floods of new data coming from the instruments, the lab instruments, measurements of the sky, all the things I've talked about, and hopefully some of this will tell us a bit about how all of this works. And there are a flood of new ideas, flood of new data. There's an exciting few years ahead, and we're hoping we can kind of, like this old medieval drawing, we can kind of break through what we understand about the universe to see a bit of the new physics that lies beyond. So that's all I had. Thank you.
Why do you not want to talk about the one detection?
Well, you see, why do I not want to talk about the one detection of dark matter? There is this one instrument called DAMA. Dark matter is DAMA. It's an Italian experiment with some Chinese collaborators. It operated years and years ago. It operated in a mine called Gran Sasso in Italy. And it operated for many years. And it saw a fluctuation in its event rate. So they can't tell what kind of particle is hitting their detector, but they do see that the rate goes up and down every year. It goes high in the summer, low in the winter. This could be all kinds of things, but they think it could be dark matter. Because the Earth, as the Earth orbits the sun, it moves there's kind of a wind of dark matter, and we move with the wind and against the wind. In the summer, we should see more events, in the winter, less. And they see this. However, no one else has seen any similar signal like this. No one has repeated that exact experiment, and that's a big effort here. We have one faculty member here who's involved in a collaboration called DMICE, which is trying to repeat this experiment at a different location. But there are various other things that vary and that are higher in the summer and lower in the winter. Perhaps you can think of some. No one quite understands how this signal could be caused by it, but I would say by and large nobody is convinced this is dark matter. That's the one experiment. Smash theory, you're going to have to remind me. I know I've heard that acronym and I can't remember right now. You're quizzing me on stuff that was in the news a week ago. This is a particular theory of that tries to solve dark matter and dark energy, if I recall.
Well, so it's 5 problems, and you add 5 things to solve 5 problems. So, so it's a unified theory of inflation, dark matter, and solves the strong CP problem in QCD. But there's 5 problems, you add 5 things, so it's not really.
It's real good PR. Maybe it's right, but it slices, it dices, it makes French fries in 12 different sizes, but that doesn't mean it's true. It's an attempt to explain many, many different things. I don't know of any experimental tests usefully that could say anything.
Yeah, have they been able to measure the effect dark matter has on the motion of objects in our own solar system?
That's a good question. So the question is, have we been able to measure the effect that dark matter has on the motions of objects within our own solar system? And there should be some small effect. But the answer is no, and it's because the effect is very small. Our universe, dark matter matters on the scale of our galaxy, right, or the universe. But in our solar neighborhood, the gravitational pull of the sun and planets is so much stronger than the pull of dark matter. Because there's so much, we're in a dense place. Because we're near the sun, it's very hard to disentangle a tiny effect like dark matter's pull from the large objects nearby. It's trying to listen to a whisper next to a loudspeaker. You just can't detect that tiny effect. There are people who do things like monitor the positions and speeds of space probes, like Voyager and Pioneer, that we have sent out into space, and make sure they follow the path that we expect. If they didn't, that might mean there was some additional gravity pulling on them. So far, there is no convincing evidence of an anomaly. So we have looked for this, it has not been seen, but it's not surprising it hasn't been seen. It should be very small on this compared to the large forces tugging on things in our solar system.
Yeah. Is it fair to say that there's more dark matter where there's more gravitational field?
Is it fair to say that there's more dark matter where there's more gravitational field?
Directly proportionate?
It varies a bit. So as I showed you so in general, dark matter is most of the mass in the universe, and so it provides most of the gravitational pull. So in general, that's true. But there are places, like I showed you with the bullet cluster, where the ratio of dark matter and ordinary matter is different. So it turns out the center of our galaxy has so many stars. Tens in the distance between us and the nearest star, there's millions of stars in the center of the galaxy. It's very, very dense. And so in that area, the ordinary matter is the overwhelming source of gravity. It's not until you get to the outskirts of the galaxy where the dark matter wins, so to speak. So there's different areas have different ratios. On the largest scales, on the scales shown here, dark matter wins. But in smaller areas, sometimes the ordinary matter is dominant.
But the delta predicts dark matter.
But the what?
The delta between the observed mass and the gravity.
Yes.
I don't understand your personal research strategy.
I question that myself sometimes.
So are you agnostic and simply looking and hope when you see something that's not standard model, it might be that? Or do you actually derive things from the theories and then look specifically for those?
So that's a good question. So the question is, when we look for dark matter, so I should say this isn't what I've been doing mostly nowadays here at U of I, but it is what I did in graduate school. And so we work on these detectors underground for dark matter. The question is whether there are particular theoretical motivations that lead you to look for one kind of signature. And the answer is yes and no. So for example, this kind of detector is predicated on the idea that a dark matter particle should knock a nucleus out of place rather than an electron. That would happen if the dark matter particle was heavy and slow moving. It should be slow moving. We know it has to be because otherwise small galaxies wouldn't form, but it doesn't have to be heavy. It could be a light particle. And a light particle would knock electrons out of their orbits. A heavy particle would knock nuclei out of their orbits. So in that sense, there was a big theoretical motivation for a model called weakly interacting massive particles, WIMPs. The competing model was actually called MACHOs. But the WIMP model has had a lot of success, and it predicts you should see something exactly like this. And that's why we spent all this money to build this kind of detector. But there are other models. So this kind of radio detector I showed you in the next slide is looking for an entirely different model called Naxion. And the astrophysical searches, the searches for how the motions of the different stars in the galaxy behave, they don't care what kind of dark matter I'm looking for. So some searches are very specific to a particular theory, some are more general. There's a range.
Dark matter related to dark energy like ordinary matter?
Is dark matter related to dark energy the way ordinary matter and energy are? So this question, probably not surprisingly, won't get asked a lot. And the answer is, we don't know. Because how could I convincingly answer when I don't know what this is and I don't know what that is? Like, maybe they're related. But there's no reason for them to be related. There's no experimental evidence that they are related. There are some theories where they are, many theories where they are not. So when we figure out what at least one of them is, maybe I'll have an answer. But right now, it could be, but we have no reason to think so.
In the very early universe, there was more or less the same amount of matter as antimatter, a little bit more matter, and it all annihilated. And what we see around us, is there any evidence that it did or didn't happen with dark matter?
Oh, now you're getting tricky. Okay, so that's a technical question. So the technical question here dates back to the very, very, very earliest moments here, where at some point there should have been, we think, equal amounts of matter and antimatter. And those annihilated away, and a small amount was left behind. There was some asymmetry. There was a little more matter at the beginning, a little less antimatter, and we're left with, we are the detritus of that annihilation. The question is, did this happen for dark matter as well? Was there such a thing as anti-dark matter? Was there dark matter annihilation? It depends on the theory. So in many theories, like the WIMP model I talked about, dark matter is actually its own antiparticle. And when it's dense, it does annihilate. And so it should have been that there was a lot of dark matter early on, and then it annihilated away, and there's only a little bit left. And the reason people got excited about WIMP dark matter, and people got excited about building experiments like I worked on, why we spent time on this one particular kind of dark matter, is that in that model, you naturally get the right amount. It annihilates at the right amount of it annihilates that the leftovers equal approximately what we see today. So it depends. There are other theories called asymmetric dark matter where there actually is matter and antimatter of dark matter, and there was a different amount of one rather than the other, and we see the leftovers. Depends on the theory. But the annihilation, in most models, how the annihilation happened is a crucial part of explaining why we have the amount we have. But as usual, since I don't know what it is, I can't give a definitive answer about exactly what it did at 10 to the minus lots of seconds.
Like you said, how Einstein said that you can imagine space and time as a little grid like that. Well, like any blanket or anything, if you drop a heavy enough object on it, it'll have a rip right through it. Well, what if this sounds like a crazy idea, but what if dark matter is like a gravity-loving particle that comes from the effects of too much concentration on a certain point in a space-time location? So, like, space is curved, but instead it's like a hole that flattens it out on a certain scale.
So I think you're asking, is dark matter related to some effect of really bad distortions of space-time? Like a place where you almost punch through the fabric kind of thing. The thing I can think of most related to that are black holes. So a black hole is a place where you get so much matter in one place, you make such a nasty dent in here that even light cannot escape. It's a rather nasty wrinkle in space-time. There have been people who speculated that black holes, there are tons of little black holes around the universe, and those constitute dark matter, those little puckers of space-time. They're invisible, which is very convenient. The problem becomes with that is, how did you make the black holes? If you made them from ordinary matter, well, remember, from looking at the light elements and looking at the CMB and simulations, let me get back to the chart here. We know that most of the matter in the universe, even back then, even back in the early days, most of the matter in the universe was not ordinary matter. So black holes, you have to have made them somehow in the early universe not from ordinary matter. And there are ways in like the Big Bang itself you could make a lot of black holes. There are theories that say that this could be the dark matter, but there are various challenges with this.
There's a new theory about how that the Big Bang has singularity. The only other singularity we know is a black hole, and that the universe came from a three-dimensional black hole from the remains of a four-dimensional star collapsing inside of itself. Couldn't that provide like many black holes all around it?
So the question is about how the universe's, I think about how the universe's birth relates to black holes. There's sort of a similarity. They're both nasty, dense spots with strange properties. There are some deep relationships there, but now you're getting beyond my expertise of exactly what could happen in that kind of early universe. So, I can say maybe, but in most situations, no, the early universe is a little bit different than a black hole in most theories.
Yeah, this one right at the back. The infrared picture of the universe, the voids, are there stars in?
So that's a good question. So if I go back, so when you said infrared picture, do you mean this one? Okay, so this is a picture of a simulation of the matter density of the universe. So it's not a photo, it's a simulation, if you could see with dark matter eyes. You see there are voids. There are these black areas which are like holes in a sponge where there isn't much stuff. The question is, are there stars there? And people look for this. It's actually very hard because the voids are far away. You can see a galaxy far away, but an individual star a billion light years away is hard to see. There is some evidence that there are some rogue stars out there, but and there's actually an active topic of exactly what fraction of stars are free of galaxies. But most people think most stars live comfortably in the shiny spots here in the galaxies. But there surely are some out in the voids. Usually they got hurled away when two galaxies collide. Some of the stars get hurled away and can sail quite far away. They could be, but they're very dim. So actually my office mate, when I was at Caltech, the guy I shared an office with, who's now a professor at Rochester, he built an infrared telescope to look for the infrared glow of stars and gas out in the voids. And the result was a little inconclusive. It's very hard. But people do look for this. That's exactly right. That's an interesting question. So the question is, we see dark energy in our universe. We see the expansion of our universe accelerating. Could that be because there are other universes outside? There are regions that we can't see beyond our horizon, so far away the light hasn't reached us, but their gravity is pulling on our universe. Like our universe is expanding and it's going faster because it's getting sucked outward by these other massive areas around us. And this is, again, a topic of some debate in the literature. Some people think that what if we're in a little pocket of the bigger universe that has less stuff than the surroundings, and that could be faking the acceleration. I think most theorists think that doesn't work, but there are occasional papers that show up every now and then where someone argues that this is so.
You have to be very finely tuned in the middle of a void, I think.
It's really hard to set up a situation where you fake the signal. What hope is there of fitting dark matter into the standard model? Well, it depends what you mean. So it doesn't fit, as I showed, it isn't any one of the particular particles that we know of. However, as a particle physicist will tell you, there are some problems with the standard model. There are some, we know all of these particles, we know these forces, we can calculate with high precision everything we see in accelerators, but there are some things we don't understand. And so, like as Peter was saying, you can try to explain various mysteries by adding new particles that we haven't seen. And one of those particles might be dark matter. So in fact, one of the best evidences we have that the standard model is incomplete, there must be new physical processes, is that there's dark matter. There's dark matter and dark energy. There's at least one or two new things that are not in this model. And so there are theorists who think about how those things might relate and what we might see in experiments. What fine details might be different in our experiments caused by whatever new particles constitute dark matter. So there's sort of dark matters over here someplace, and theorists, including some in our department, Professor Jesse Shelton among others, are trying to think about different ways that dark matter could interact with our particles and things we might look for in experiments. Yes?
The experimental physicist, these endeavors are very expensive, and I assume most of the money comes from government funding. How are you able to continue to convince the non-scientists and anti-scientists in the legislature that it's worth funding?
What a timely question. So the question is, all of this stuff costs money, particularly the experiments, but all of us, even theorists, need to eat. And so we require money, and money mostly comes from the federal government, though there is there's more and more private funding nowadays, but still not enough. It's mostly federal government funding from places like the National Science Foundation, NASA, the Department of Energy, who fund these experiments, and equivalent agencies in Europe, for example, and other countries. How do we continue to convince people that these are worth funding and that they should keep paying for people like us to do what we've been doing? One of the answers is by having events like this, where hopefully, when it comes time, and boy, is it coming up pretty quick, to vote, you may remember that thing that guy up on the stage was talking about sounded kind of cool, and maybe science funding is a good idea. And maybe that would affect who wants to choose an election. It might affect, someone might write their congressman and say, I like funding science. Having people like you interested is one of the ways we survive. And we also talk to congressmen. There are various organizations with that terrible name, lobbying. We try and make our case that this is a useful thing to do with money. Yes, these are expensive experiments, but it depends what you compare them to. The entire National Science Foundation's budget for an entire year is what, $3 billion? A few billion dollars. Sounds like a lot. It's a few bucks per person. But $3 billion, boy, you can't even buy a fighter plane for that. It depends compared to other things the government spends money on, it's actually a very small amount. So we talk to people like you is the way we do this.
All right, let's have one last question.
In the pie chart you showed for distribution of everything in the universe, dark matter. I'm wondering what's the basis for this distribution? Is it based on, but we are dealing with different things. Is it mass? Is it energy? Is it based on gravitational measure? What's the basis for finding this distribution?
Okay, so I think you're asking, what am I plotting in this pie chart? So I have said 5% of the stuff, 26% of the stuff. What does stuff mean? In this case, it means energy density. And they're related. Mass and energy are related by that Einstein expression, E equals mc squared. And so I can sort of lump them together in the same budget. I can count the energy and the mass as one budget of how much mass energy, how much stuff is there in each average cubic meter of the universe. And this is saying when I average over the whole universe, billions of light years in scale, I find that about 2/3 of the universe's total energy is this stuff, about 1/4 is this stuff, and about 5% is stuff we understand.
But it's based on the gravitational measurements.
There's a bunch of, so one of the ways, is this based on the gravitational measurements? So one way of answering that is it's based on many measurements. So I showed this kind of cryptic plot toward the end, which this is amount of dark energy. So you see this is 0.6, 0.8, that's the 68% that I talked about, corresponds to about here. The dark matter, I said 26 point something percent plus another 5%, that's a total of 31% matter. Well, that's about there. So the way we actually combine different measurements that are good at measuring different combinations of this energy density. And where they overlap, these preferred regions, we get the answer that I put in that pie chart. There's some uncertainty. Maybe it's not 68%, maybe it's 69 or 67, but we actually have to combine multiple lines of evidence that are good at measuring different combinations of these numbers. And together we build the pie chart. The beautiful part is there's a consistency. It didn't have to be true that those three overlapped. If they didn't overlap, and many other measurements I'm not showing, overlap and give us that one answer in that pie chart, those one set of numbers, it could have been that we had a totally wrong model, none of it made sense, these landed all over the place, and we have to rethink. But it does really seem like there's these three kinds of stuff, and we do have a consistent measure of how much there are of each. We just don't know what they are.
All right, there's one particularly eager question that we'll have right at the end.
So since a black hole is so heavy and has so much mass, wouldn't it have a lot more dark matter surrounding it than other objects?
Okay, so that's an interesting question. So since black holes have a lot of mass, have a lot of gravity, they pull on stuff, would they also have a lot of dark matter in their neighborhood? I think is your question?
Yeah.
And somewhat, but not overwhelmingly. So a black hole feels pretty different when you're right near it, but if you go far away from a black hole, it is a mass like anything else. So if our sun were to turn into a black hole, it would be bad for us in many ways, but it would not suck the planets in. Earth would continue in its orbit totally the same as always. It doesn't care whether the mass in the center is a black hole or something else. It would stay in its orbit. And similarly, the dark matter doesn't get, sucked into the black hole from far away. It will continue its orbit. The black hole will collect some dark matter, but it won't collect huge disproportionate amounts, probably. Depends on how much dark matter is in the area when the black hole is formed.
And would the dark matter actually get sucked into the black hole?
Just like anything else, if its orbit gets close enough, it'll eventually, the orbit, it encounters this sort of very bent space-time. Dark matter that gets too close might fall in just like anything else.
All right, well, let's thank Jeff for a wonderful talk.